So maybe now would be a good time to remind you. So our confidence interval for mu when sigma was known. Remember, confidence intervals are usually the estimate. So in this case, it was x bar plus or minus the critical value. And the critical value in that case followed a standard normal distribution. And then my estimated standard error was sigma over the square root of n, right? That was the confidence interval we were using before. So now when we move into using a confidence interval and we don't know what sigma is, so again, the big change here, okay, is that we've replaced this sigma with s. And by doing so, now our critical value, this z is going to change to a t distribution. So you'll notice the area in the right-hand tail is still alpha over 2. So nothing's changed about that. But because we've moved from a z to a t distribution, we now have to specify a degrees of freedom, right? So maybe I should just write this in to be really clear, right? So this is the area in the right tail, okay? And this here, the n minus 1, that's our degrees of freedom. Which I usually write df, okay? But other than that, it's really gonna kind of work the same way. So our first taste at sort of applying this t-distribution, we're gonna think about this, the context of our example, where we're looking at mercury content in dolphin mussels. So there's these riso dolphins. I think they're pretty common in Japan. Or maybe, sorry, I don't want to say they're common, but they're found in Japan. Or sort of elevated mercury levels in fish is a concern, one for the dolphins themselves, but occasionally other animals, including humans, occasionally eat them. And so we want to be sort of concerned about this mercury content in the dolphin because whatever consumes them, whether that's a human or another predator, they're also consuming that mercury. Okay, so mercury in this case is going to be measured in micrograms per wet gram. That's just a pretty common unit of measurement when we're looking at these kinds of things. So it says identify a 95% confidence interval for the average mercury content in the dolphin mussel from a sample of 19 riso dolphins in the Taiwan area in Japan. Okay, and so they've given us the data here. This is our sample mean, x bar, right? This is our sample standard deviation, and this is our sample size n. So let me just write out the formula here was x bar plus or minus t alpha over 2 n minus 1. That's our critical value, and then our standard error is s over the square root of n. Okay, so from there, we just sort of need to plug some pieces in. So we can plug in the x bar, that's not so bad, 4.4. Okay, the s is 2.3 divided by the square root of n, which is 19. But here, this t, we're gonna have to do a little bit of extra work. So first of all, okay, if this is a 95% confidence interval, that means that my alpha, okay, is going to be 5%, right? That's always 1 minus. So if alpha is 5%, then alpha over 2, if I have to take that probability and divide it into 2 tails, is going to be 0.025. Okay, so I'm looking for the t distribution with 0.025 in the right-hand tail. Okay, and in this case, my degrees of freedom is going to be n minus 1. So in this case, it's going to be 19 minus 1, which is 18. Okay, so maybe I'll just, this piece here, right? If I wanted to work that out, let's draw ourselves a little picture. Okay, so there's our t distribution with 18 degrees of freedom. I want to know the value here, where this area to the right is 0.025. Okay, and we talked about how to do this using R. I'm just going to erase these here. And so if we have the probability and we want the area, our function is going to be Q, and then because it's on a t distribution, it's T. So QT, we're going to feed it in the area, 0.025. We're going to feed it in the degrees of freedom, which is 18. And then I'm also going to do lower dot tail is equal to false to make sure that I get the area to the right and not the area to the left. So I'm going to take that and plug that into R. So here I am in R. We're going to do QT 0.025, oops, 5. And then we've got 18 and lower dot tail is equal to false. And that tells me 2.100. And again, I usually round, so 2.101 or something like that. .101 if I'm rounding, okay? So now we've got 4.4 plus or minus 2.101 and then times 2.3 divided by the square root of 19, okay? So my confidence interval, let's maybe divide it up. Let's kind of work out what that number is there, the 2 point whatever. So that gives me 4.4 plus or minus, and when I plug that into my calculator, I got 1.09 if I round. Okay. Usually I try to carry the full numbers through as much as I can, but it's nice to round as we go just for ease of looking at this thing. Oh, I forgot, sorry, 1.109, there we go. And then from there, then you're gonna write out the two values. So it's always gonna be the lower value is always the minus value, okay? And the upper value is going to be when we add the value. So that's gonna mean that my lower bound here is 3.291 when I round, and my upper value is 5.509 when I round. Okay. And make sure that you've got those in the right order. I've been noticing some students mixing up the order, so make sure that the lower value, the one that comes from the minus, comes on the left side, and the one that's the larger number with the plus sign is on the right. That's important formatting. And so that means that we're going to say, if we were to conclude here, we are 95% confident that the true mean, this was a mercury content in the dolphins is between 3.291 and 5.509. So that would be how I would interpret it. And note here that I use the word confident, and I'm using that in the strict statistical sense, meaning that, you know, if we were to repeat this repeated sampling of 19 dolphins, we'd expect that 95 of those intervals to contain the true population mean, and 5% of those intervals wouldn't. That's sort of the strict interpretation. So hopefully that example helps.